Hi everyone, I'm Janjia from Nanyang Technological University. Today I'm going to present our work, Handling Gaps for Vector Graphics Coloring. The other two authors of this paper are Professor Xiaopo Sun from NTU and Mr. Liu Hongzhe, who is a professional artist.
Okay, what are gaps and how are they produced? Here we illustrate some scenarios. In this example, we see many gaps in this drawing. They are intended because of the drawing style, such as minimalist neat sketch. And gaps can be produced unknowingly. When user draws, strokes may not precisely connect to other strokes. Besides, there are other scenarios such as image interpolation based on keyframes. We can see gaps in intermediate frames. When we want to color a drawing with gaps, regions cannot be colored using flat fill because color leaks through gaps. Hence, the major problem is regions cannot be colored. How to handle this? There are some approaches such as live paint and smart coloring that require users to input sizes for gap closing. It is also widely in other 2D drawing programs. Some other approaches have been proposed as well. Here we show a triangulation-based method, which is independent of gap size. However, there are still challenges. The first one is gap size sensitivity. For example, like this, here is a gap. If we close them with two different input sizes, the results are different. So that therefore, user may color a drawing with careful selection of size. This second one is the detection of end-to-end connection. Some methods handle gap points individually, therefore end-to-end connection may not be correctly detected. The third one is appearance. As we can see, although our gaps are closed, we can see bands a lot, which we call sharp bands. However, they are usually supposed to be smoothly connected. When a gap is big, this problem becomes more significant. We propose a method with 4 steps to resolve these issues. The first step is gap size computation. Next, we cluster gap points. Then we do gap closing. And the last step is coloring. Now is the first step, gap size computation. In our method, we call such dangling your endpoints as gap points. To close a gap, we just need to find a point to connect to. But here, which one is the best one? Let's look at them. For this one, the shortest one, it is short, but it has a sharp bend. But for this longest one, it is very smooth, but it is but it's too long. It sometimes results in a wrong connection. Therefore, in our method, we compute a size, and then we will find a point within the size. To compute a size for a gap point, we consider two local clues, which are the nearest point and the extensional point. The nearest point usually indicates the destination stroke to connect to. However, sometimes it results in sharp bends. For the extensional point, it preserves smoothness, but it can be far away, which means it may be a wrong connection. Therefore, the destination point should not deviate too much from the gap point. So we compute sizes by balancing both the distance and angle. We propose these two weighted terms, and P candy is just a random point. If it is very far away from the gap point, then these terms will be very large, and vice versa. We propose an energy function that takes both terms into consideration. The objective is to find a point to minimize this function so that a gap point size can be found. After computing gap sizes, we come to step 2, clustering gap points. The purpose of clustering is to group gap points that should be considered as a whole where end-to-end connections may exist. Our clustering method is developed based on simple observation. We can see here a set of gap points and we look at the 3 points. D1 is much shorter than D2, which means that the upper gap point is very unlikely to be considered together with the lower 2 gap points. In other words, if 2 gap points are very close, they are very likely to be a cluster. For a set of gap points, we firstly construct a minimum spanning tree. The reason is a minimum spanning tree tries to connect all the gap points with the shortest lines, and it can represent the spatial relationship of these points. Then we start iterative edge check. The objective is to determine if an edge should be added or not. We do it by computing the energy change. When this step is done, some of the edges will be dropped. Finally, linked points become one cluster so that the gap points will be clustered. Now we have clustered gap points. The next step is to close them. In this step, clusters will be processed one by one. Gap points in one cluster will be considered as a whole. Firstly, we introduce gap types. Generally, there are 2 types, end-to-end connection and T-junction. In our method, we call them V connection and T connection. However, there are 2 challenges here. First one, a cluster of gap points can be closed in different ways. Depending on context, we cannot determine which one is better, which one is not. And then a V connection may connect 2 points, 3 points, or 4 points. In previous methods, they only handle 2-point cases. So we propose our method with 2 steps. The first step, we detect V connections, and then we detect T connections after that. A V gap should connect as many gap points as possible. Now we will introduce how to find V connection and T connection from a cluster. As we introduced earlier, some previous methods produce non-smooth results. Therefore, we propose an energy function to measure the goodness of the destination point, PT. As this energy function is an increasing function, when the destination point deviates drastically, the energy will be high. For one cluster, how do we know if there exists a V connection? Here we introduce a concept called solution area. Theta d represents the maximum allowed angle deviation of a gap point in V connection detection. For a cluster of gap points, we can find their solution areas. Then we find the overlapping areas shared by most of the gap points. For example, a green area in the middle is shared by 3 gap points, so that n max is 3. Then we find a point within the overlapping area that minimizes the energy function here. Because this energy function is convex, so it is very easy to find its solution. Then we come to T connection. We directly use the energy function. We also find a point to minimize this this function. Since T connections the destination point must be on a stroke, the solution is limited to the segments within the gap points range controlled by its size, like this. Like what we mentioned before, gap closing depends on our context, so that the result may not be always ideal. So we provide two ways for users to manipulate the gap closing result. The first one is to choose to use smooth curves or straight lines to fill a gap. This, as the second one, is to manually cluster gap points for closing. Now is the fourth step, coloring. Drawing. In our method, gaps are closed by curves with no stroke wave like this. If both sides are painted with the same color, the gap is visually reopened like this. Therefore, although we close some intended gaps, such as this, they can be resolved when coloring, shown here. We have done experiments to compare our method with some state-of-the-art methods in the as mentioned earlier, a challenge of gap closing is gap size sensitivity. For example, in Krita, when gap size changes, the results are not consistent, like this. In our method, we compute a size so that user does not have to worry about the selection of appropriate gap sizes. But as we can see from the results, our method performs well. The gap sizes are properly closed. The second challenge is end-to-end connection. Our method has a clustering step so that nearby points will be considered as a whole. Hence, end-to-end connections can be properly detected. Hence, here are our results, for example, like this, and this, and this. End-to-end connections can be correctly detected and closed. The third challenge is appearance and stroke connection. Since we use energy functions for gap detection, the destination point will not deviate too much from a gap point. Well, as we can see, our method is smoother than the other two, like this. Meanwhile, our method also helps prevent stroke connection, like this. We also apply our method to color the different types of drawings with more strokes and gap points. Our method still works well in handling this. We have two major limitations. The first one is wrong gap closing result due to incorrect clustering. We can see here we have 4 gap points here. Then the gap size of this point is much smaller than its adjacent edges, so that these points will be wrongly clustered. There are 4 clusters and they will be handled independently, so the result is wrong. And the second limitation is that we cannot determine the gap between non-gap points. For example, like this, the reason is we only consider the dangling stroke endpoints. In the future, we would like to continue the work from the following 3 directions. Firstly, we would like to use context information for example, like strokes as sequence information to improve our gap point clustering. For the triangulation-based approach, it can be a solution to the gap between non-gap points. And we would like to use more frames to improve our gap point analysis. Thank you. This is the end of my presentation. Thank you for your attention.